All right, so if we want to try and sketch our original function from the derivative graph that's present, you just got to really focus on where the gradient or where the graph is above the axis or below the axis. So for example, just in here in the yellow, all this section represents negative gradient. Okay, so the line given is the gradient graph, so that yellow section represents a negative gradient. So key points where the derivative crosses the axis, so at -1, 1, and 3. So I just do a little, it's not an asymptote, but a little dotted line to suggest that somewhere along that vertical line is a key point. It's a turning point, isn't it? So obviously to the left of that line from -1, or from negative infinity to -1, we have a negative slope. So I've just drawn a negative slope somewhere along there to the gradient. It could be anywhere along that line, all right? So then to the right of that slope, to the right of that little dotted line between -1 and +1, we have the blue section of the graph, which I'm highlighting now, and that represents a positive gradient. So my gradient is increasing. My equation is increasing in that section until it turns somewhere along the line x equal to 1. And then again, down here is where our negative line is. So that negative, where it's below the axis from the actual drawn graph. So you can see there in red where I've drawn a section of the graph that has a negative gradient until it gets back to 0. And then obviously to the right, the gradient is above the line. So the function is above the line. And so I draw a positive gradient slope, all right? I guess the other thing to keep in mind for this particular graph in particular, it's a cubic graph. It's basically a cubic graph. So I should end up with something that looks a little bit like a quartic. And so if I just flow that through, the graph that I've drawn is got a basic quartic look. And so that should be a reasonable, a possible graph for the function f of x, all right? Let's go back a step now. Obviously, I've been given the derivative dy dx equals, so then my antiderivative, to get the function y, if I integrate both sides, I'll get y equals the antiderivative of the function with respect to x. Let's remember that integral sign there, just sort of colouring in now, belongs with dx. You can't have one without the other. Then once we anti-differentiate, both those symbols disappear, add to the power and divide by the power, etc. So hopefully we know the process, plus c. So here's my general rule there. Okay, that's an antiderivative. If I want the specific antiderivative, in other words, the specific function, I substitute the 0.10 in. So at x equal to 1, y is equal to 0. If I substitute that in, hopefully I get c equal to -2, which means then I can just draw my original function.